When
Hmm.
um, when the waves kind of like form in multiple directions, like
Mm-hmm.
in 90 degrees.
Not at 90 degree all the time. Again, you misunderstood this. Which are in phase. All the points which are in phase and giving a shape, uh, shapical form to the wave. Okay.
Yes, ma'am.
That is known as basically the wave fronts.
Oh,
Okay. Yesterday also I had told you that all the points which are in phase and they give a shape to the wave. Done? Like some are lying at 90 degrees, some are lying at 89 degrees, some are lying at 87 degree, and like that one wave has been formed
yes, ma'am.
and it gives a pattern.
Yes, ma'am.
Done? So we
Yes,
have cylindrical wave fronts, we have circular wave fronts. Done?
yes, ma'am.
Okay. Now after that, we have Huygens construction. So what is Huygens construction basically? We can think of a wavefront that it has been made up of infinite number of new centers of disturbance. Okay,
Yes, ma'am.
that every wavefront plays the role, Akshita, for the secondary, as a source of like primary and the secondary disturbance in the medium, right? From there also you can see that the another waveform has been created. Understood?
Yes, ma'am.
Okay. And each disturbance creates its own wavelet. Okay. That is wavelet. Now it will be what? That I'll show you. Just give me a sec. Okay. Have a look at this picture, Akshata, that I am pasting here. Okay. Check. Can you see this picture? Akshata, are you there?
Hello, ma'am. Yes, ma'am. Yes, ma'am.
Yeah. So I am saying, can you see this picture clearly?
Yes, ma'am.
Okay. So what I am telling is that uh, every wavefront basically see what are the points that are lying on this line are nothing but wavefronts. What are the points that are lying on this wavefronts? Here also lay wavefronts. The wavefronts. The wavefronts. Understood?
Yes, ma'am.
Okay. Now try to understand that each disturbance creates its own wavelet and that progresses in the direction of the wave. Done. Wavelet means if suppose one wave is created like this, let's sketch out one point that can create its own disturbance.
Yes, ma'am.
Okay. Now these points which are created by it, it will be wavelet. Okay.
Yes, ma'am.
Okay. So the wavefront is made up of the sum of these wavelets. here all, if I take this one pattern, so all these things are wavelets. Done?
Yes, ma'am.
Done. And the thorough condition which has been formed is known as wavefront. Done?
Yes, ma'am.
So now here you can see in your figure that basically circular and plane wavefronts propagate according to the construction. Let me show you that also. Okay, how is it looks like? Okay, can you see this diagram? So it's a straight wavefront, it's a semicircular wavefront, right?
Yes. Yes, ma'am.
And in each wavefront, one more new circles has been created. That are the wavelets.
Yes, ma'am.
Okay. So here, the Huygens construction treats the wavefront as if it is made up of infinite number of small point. Okay. And that only
Yes.
but Huygens gave no explanation that propagation is only forward, but the model correctly predicts the laws of the reflection and the laws of refraction. Okay. He is not able
Yes.
to say that why they are moving only in the forward direction, aren't they are coming back, or can they come back? But he had thoroughly explained the laws of reflection and refraction in all type of waves. Understood?
Yes, ma'am.
Okay. Now, Snell's law was the result of many experiments, okay, measuring the angle of light rays passing through one medium to another medium, right? And the result gives the path with the shortest time.
Yes, ma'am.
Hmm. Now, a result that is in agreement with Einstein's theory of relativity. Basically, it was contradicting, I should say aligning. Okay, not contradicting, but it was aligning with the Einstein's theory of relativity. And there can be more than one theory to explain the phenomena, but they must give consistent predictions. Okay. Now, leave all these points. It's not very much important, but yeah, we can go for the topic which is reflection of the water waves. Okay, let's do study for the reflection of water waves and how does it consist of. So basically what happens is when a wavefront hits a barrier, like here I am having a wavefront and it is hitting this barrier. Can you see?
Yes, ma'am.
Okay. Now will behave as a series of wavelets. Check how many new wavefronts have been created. Many.
Yes, ma'am.
Out of this one, how many wavefronts have got created? Many, right?
Yes, ma'am.
So it behaves as a source of creating many wavelets. Okay. Now, what happens is a circular wavefront is reflected as a circular wavefront that appears to be originating from the point behind the barrier. Okay, as if you can see over here. See, I will just show you this particular phenomena happening. Like, see, if I look at this particular wavefront, here the barrier is there, which is creating. First figure, though you understood, no? Just check over
Yes.
here. It's a circular wavefront, and when it collides with any barrier, it creates many wavelets. Secondary, and I should say many wavefront. You can see over here many patterns, right?
Yes,
Due
ma'am.
to reflection. But if you talk about plain wavefronts, the single wavefront seems like it is going in the back of this particular barrier. Okay,
Yes, ma'am.
making sense? See, here it
Yes.
is coming in, incidenting, here it is reflecting back.
Yes, ma'am.
Okay, done. So this is reflection pattern which has been shown by the wavefront.
Yes, ma'am.
Done. Now after this, we do have refraction pattern also. Now, what happens in the refraction pattern of the wave? Let me show you that thing also. Okay. So, refraction follows the law of refraction. First thing, that when it travels from rarer medium to denser medium, it travels towards the center. Okay.
Yes, ma'am.
Second rule is from denser to rarer, it will be traveling away from the normal. Okay. Third thing, sin I over sin R will give you the refractive index of that medium. Okay. Done. Now, in the
Yes.
case of waterways, if I tell you, it's very, very simple, Akshita, that suppose here is my uh, barrier line, and here I am having the shallow water, here I am having the deep water. I had told you this thing earlier also, that shallow water behaves like a denser medium for the particular wave, okay, of water, whereas deep water act as rarer medium. Okay. So in the
Yes.
deep water, you will find the speed of the wave is very, very huge. Also, their wavelengths is very, very big in comparison to the shallow water, where the wave have very small, small wavelengths, and here the speed is also slow. So in the shallow water, V is also slow and your wavelength is also small. Whereas in deep water, wavelength is also high and the speed is also high. Making sense?
Yes, ma'am.
Any doubts?
No, ma'am. Once
Done.
again.
Okay. Yeah.
Yes, ma'am.
Are you done?
Yes, ma'am.
Okay, so this is the case of wavefront that you can see when it is incidenting, it seems to be refracted. Okay, from where? From the deep water to the shallow water like this. Okay, and if it is a straight wavefront, then you can see it is traveling like this. So here you can even draw the normal line. So from deep water, that is from rarer to denser, it will move towards the center. So you can see here, this is the incident line which is moving towards the center. And even you just have to join these wave fronts in such a way that their wavelength needs to be small in the case of shallow water. Done?
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. And here you can see wave has been incidented. Okay. When it comes out, okay, what happens is the wavelets are added up to the reflected wave. So this is reflection, this is refraction. Any doubts?
No, ma'am.
Are you sure?
Yes, ma'am.
Okay, now after this, we are having Snell's law. Okay, so Snell's law was not very tough, but yeah.
It's sin I by sin R, right, ma'am?
Yeah, exactly. So, as per the Snell's law, your sin I over sin R is equal to V1 over V2. Done?
Yes, ma'am.
Any doubts in this?
No, ma'am.
Okay, so from here you can find it out. Okay. Second thing is, yeah, that is it. So let's solve one question depending upon this.
Yes, ma'am.
Other things, so you are basics, so you are aware, no?
Yes, ma'am.
Oh, very good. So let's solve one question. Give me the answer for this. Okay, I'm giving you one question. Just give me a second. Write down the answer for this. Kindly be quick.
Yes, ma'am.
Yeah. I'm just giving you 2 minutes of time. Then after that, I'm moving forward for the next topic.
Uh,
Yes.
30.1.
30.1.
35.
35 degrees the answer.
Yes, ma'am.
Did you got 35 degree?
Yes, ma'am. If I round it off, I
Okay.
would get 35.
Round off, you are getting 35. Okay. Now the next topic is diffraction of the water wave. So are you aware what is water wave?
Water waves? Yes, ma'am.
Yeah. And are you aware how the diffraction pattern has been created?
I have an idea, ma'am. Uh, like it has a, like it, oh, I don't know, like, I have an idea, but I'm not sure how to explain it. It, the water where, like, it spreads out and it opens up, and then, uh, something like, I don't remember an exact
Go
definition.
ahead, I'm listening.
I don't remember an exact definition, but there is a small what path difference. So the path difference, and it spreads out, and there will be diffraction. Is that is that it?
Okay. No. Basically, the bending of the waves at the corners whenever it passes through any slit is known as diffraction pattern. Okay.
Okay.
Suppose it is passing through any slit. Let me show you that part also. And here we are only discussing right now about the water waves, which behaves like both. longitudinal and transverse. Clear?
Yes, ma'am.
Okay, so let me show you that pattern also. Check. This is the diffraction of the water waves. Okay. So when the wavelength and the slit width is same, you will see the maximum diffraction pattern to be arriving. Suppose from here the water waves are going like this. Okay. After going from here, the amount of wavelength and the amount of slit width is same. Hence, you will see the maximum diffraction pattern to be happening. Understood?
Yes, ma'am.
But here, suppose the wavelength is like this, that is smaller in comparison to your width. Your wavelength is this, right? And it
Yes,
is smaller. So when your wavelength is smaller than the distance or the width of the slit, I should say, okay, then you will see the bending only at the corners. And when the wavelength is similar to the width of the slit, you will see the maximum diffraction pattern. Understood or not?
yes.
Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. Now let's move for the next topic.
Yes, ma'am.
Now, waves also get diffracted by the objects or by the edges. Okay. Something like this also. If some hindrance has been or the obstacle is found, they can diffract like this also. Okay.
Yes, ma'am.
See here, it's an obstacle. Already the wave is passing through. So from here you will see the cuts and the pattern will be happening with the bendings, and this bending will be the diffraction pattern. Understood?
Yes, ma'am.
Okay, now after this, our next topic is interference. Okay, already I had explained you many things about interference, correct?
Yes, ma'am.
Okay, explain me one by one and be quick.
When two waves add up and uh, there will be double the wave.
Hmm.
Uh, and then if that is called constructive interference, and if there are like two waves in the opposite, like if there are like two waves uh in the opposite direction, there
Hmm.
will be destructive interference. And then if they have this if their waves are like of the same, then they will cancel out, and the displacement vector, like not the vector, the displacement wave will be zero. I'm not sure of the water wave, but the displacement wave will be zero if they are equal. uh,
Okay. Formula is to understand that.
Formulas. The 2n
Okay. For what? 2 and for what?
2n for phase.
No, you are giving half of the knowledge.
Mm,
No issue. Let me explain. Relax. Okay. So if two disturbances are suppose made at the same time in the water pool, then two different waves will be formed. Correct?
yes, ma'am.
Okay. And when these waves basically meet, they will give you out individual displacement that will add up, and they will add as a vector addition of the both. Okay.
Yes, ma'am.
Okay. So the vector addition of different displacements is known as superposition.
Yes, ma'am.
When the two waves meet, the vector addition of the individual displacement of the wave, you can write it, Akshita. The
On-
vector addition of the individual displacement of the wave is known as superposition.
yes, ma'am.
Okay. And if the frequency of the individual wave is equal, then they result that their amplitude will be constant, and hence their phase difference between the two waves will also be constant. Okay.
Yes, ma'am.
What I'm saying is, if the frequency of the individual wave is equal, then the resulting amplitude will be constant.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. And they are related to the phase difference basically in the waves. Okay. Like if they are in phase, they will create constructive interference. And when they are out of phase, they will create destructive interference. Making sense?
Yes, ma'am.
Any doubts?
No, ma'am.
Check. This is in the phase. This is also in the phase. So two-way is been formed, which is known as constructive interference. Okay, here the vector addition of the two wave I had done. This is the destructive wave. One is starting from the positive cycle, one is starting from the negative cycle. So the two out of phase wave will be created.
Yes, ma'am.
Any doubts?
No, ma'am.
Done. So now after this, let's come to the next point. So when identical point source also produce the waves on the surface of the pool, you must see a pattern which has been produced, and I can show you that pattern. Okay, just wait. Give me a second.
Yes, ma'am.
Check this pattern. Visible?
Yes, ma'am.
Okay. So suppose A and B, two stones, let's say in the rest water I had dropped at A and at B. So they both will create their own wave, and when they interfere, they will give out these patterns, out of which central bright fringe is this, then black fringe, then central bright fringe, then black fringe, then next bright fringe, then the black fringe, bright fringe, black fringe, like that. So here the black fringe is destructive and this is constructive in nature.
Yes, ma'am.
Okay, any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. Now let's say we can see that there are the regions where X and Y are also been seen in this particular wave. Unknown caller. Okay.
Yes, ma'am.
Okay. So if we look carefully at these waves which are arriving at point X and Y from A to B, we see that X that are in phase and Y they are out of phase. Can you see the 2 points?
Yes, ma'am.
See, this is the one phase.
Yes, ma'am.
Now here this is out of phase. Again it is in phase here. This is in phase. This is out of phase. So see, X is
Yes,
in phase, Y is out of phase. Correct?
yes, ma'am.
Correct? Okay.
Yes, ma'am.
So
Yes.
for constructive interference, Akshita, we have the formula of path length or the path difference. What is the path difference? Let me show you that part also. Suppose here we have one slit. It's coming like this. So here the wave pattern has been created. I'm creating one more slit. It's passed through both of them. And a new interference pattern has been observed here. For this also you will see the interference pattern
Yes, ma'am.
like this. So here at the first where the waves are intersecting in one line, you will see central bright fringe. Then at the second, when they
Yes,
are
ma'am.
crossing each other, you will see the first bright fringe. Then at the third, you will see the second bright fringe. Similarly, here also the first bright fringe. Here also
Yes.
your second bright fringe. So this is extreme left, this is extreme right. Okay. Central bright fringe will be of very high intensity, then a low intensity, then a third decreasing, and it decreases like this. Okay. So this particular thing, which is that intensity is decreasing, is known as damping of the wave. Okay.
Can you repeat the definition, ma'am?
From in the interference pattern, Okay, from the mean position to the extreme points, the decreasing intensity of the wave has been seen, which is known as damping of the wave.
Okay, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay, if you have any doubt, just do let me know. Okay, fine.
Okay, ma'am.
So this is it. And path difference, let me explain you this also. Suppose here I have two slits, let's say S1, let's say S2. So from here where they are meeting up on the screen, it is called central bright fringe, and this is the path they are traveling. This is the path they are traveling. Okay, so here what happens is, whenever I draw the wave, I don't understand why does it get rubbed up. See,
Yes, ma'am.
I think they are also interfering. Okay, so basically here you will get at the meeting point the central bright fringe. Now if I create here one wave, Akshita, I think this wave has traveled, this wave, a little longer distance. Let's find out how much. So I think this much. This much of the little longer distance it had traveled, right?
Yes, ma'am.
Okay. So this, the wave which is traveling a little longer, from this wave, this is wave 1, this is wave 2. So wave 2 is traveling longer distance to arrive at the first bright fringe in comparison to first wave. So that comparison, that difference is known as path difference. Okay.
Yes, ma'am.
Okay. And from here, how much angle it had covered more. Okay. That is known as the phase difference.
Yes, ma'am.
Okay. So
Yes, ma'am.
for constructive interference, your path difference is always n lambda, where n is a whole number. For destructive interference, your path difference is always n plus half lambda. Again, n is your whole number. Okay, you are noting it down?
Yes, ma'am.
Kindly do it fast. Done.
On screen,
Similarly,
ma'am.
here the phase difference is 2n pi.
Yes, ma'am.
Okay, and here the phase difference is 2n plus 1 pi. Okay,
Yes, ma'am.
any doubts?
No, ma'am.
Sure.
Yes, ma'am. Sure, ma'am.
Okay. Now after this, let's do study of reflection and refraction of wave in the in the case of light wave. So are you aware what is reflection and refraction of light wave?
Um, of the light wave, ma'am. I think it's the same as
Yeah. So basically the bending of light ray from any plane and smooth shiny surface at the same angle in which it is incidenting from the normal, where angle I and angle R are similar as per the law of reflection, and all the 3 points, that is the incident line, the normal line, and the refracted line, all lie in the same plane. This is basic phenomena for reflection of light.
yes,
Clear?
ma'am.
Let's
Yes, ma'am.
talk about the refraction of light wave. In this, when a light ray passes from one medium to another medium, the very first condition is the medium need to be transparent or translucent. And when it travels from one medium to another medium, it follows the rule that when it travels from rarer to denser, it will be moving towards the normal because of the density of the particles in the medium. Here is the angle theta. Okay, that is angle of refraction. Here angle of incidence is happening as per the law of refraction. Your sin I over sin r will give you the ratio of the two mediums, which is known as 1 and 2, and it is known as the refractive index of the medium.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. And similarly, when it travels from denser to rarer medium from the normal, it will bend away from the normal. Okay. That is, your angle I will be smaller than angle R. And ultimately, when we proceed for the refractive indexes formula, we will be having many formula like sin I over sin R is equal to N2 over N1. Okay. Whereas even you can write as sin I over sin R is equal to N1 over N2. You need to take care that here it is in inverse form, here it is in direct form. Okay. Also, we say that your sin I over sin R can also be equal to V1 over V2 or C over V1. Okay. Where C is the speed of light, 3 into 10 to the power of 8 meter per second. Done?
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay, let me give you one question and let's prove that actually you understood everything. Okay, do the question. Be quick.
Ray of light traveling in an air is incident on a glass block at an angle of 56 degrees. Calculate the angle of refraction with the refractive index of glasses. Sine. Ma'am, the add is one, right?
Yes.
The reflex.
Hmm. Akshita, give the answer.
1 second. 33.551.
33.5, that means 34
Ma'am?
degrees somewhere. Yeah. Am I
No.
audible?
No.
Hello. Yeah.
Hello, ma'am?
Yeah. Hello.
Hello, ma'am? Yes, ma'am.
Hello. Am I audible?
Yes, ma'am. I can hear you. I can hear you.
Okay. 34 degree.
Hello, ma'am?
Hello.
Yes, ma'am.
34 degree is the answer. Yeah.
Yes, ma'am.
Okay. Now after that, let's continue for dispersion now. Okay. Am I
Yes.
audible?
Yes, ma'am. But I
Okay.
think there is
Let's
like a
con-
timeline. There is a
okay.
slight
Okay.
time.
Okay. Okay. No issue. Let's say here I am having a prism. From here I am passing a white light and it gives out two rays, one here and one here. One is passing through like this, one is passing through like this. On the screen you will observe the Vibgyor pattern. So the splitting of white light into 7 colors, okay, when it passes through the prism, okay, this particular phenomena is known as dispersion. Understood?
Yes, ma'am.
Okay, and here you will always have the angle of deviation from the angle of from the incident line. Like here, this is the incident line. Obviously, this is the incident line. So from here they will be deviating, creating angle of deviation. So the angle of deviation will decide that which color will be formed on the screen. So angle of deviation for R is the minimum and angle of deviation for the violet color is the maximum. Okay.
Yes, ma'am.
Let's talk about the critical angle now. So for critical angle, you will be having total internal reflection happening on the screen. What is total internal reflection? Let's say here I'm having the normal line and my incident light is passing through. That is from denser to the rarer medium. Very first condition, it should travel from denser to rarer. Okay. When it is traveling, you will see it will be going away from the normal. So angle R will be greater than angle I. Okay. Let's check what happens if I increase the angle. So if I increase angle I, it will be bending more away from the normal. Okay. Like this. Suppose here again I am drawing the same pattern. Okay. So here if I give more angle of incidence, I will observe that now the angle of refraction is exactly 90 degree and it's coinciding with the surface. Done. So now this angle is known as critical angle at which the particular incident angle is giving that much of refraction that the angle of refraction is now 90 degree. Okay. Now I
Yes.
will do more after this. What will I observe is as I increase more angle of incidence, now my ray will bend in the medium itself and you will see here angle I and the angle R will be like this, nothing but 180 minus this angle. Okay. So here, this particular process will be known as TIR. So the two conditions for TIR is it should travel from denser to rarer. Second thing, your angle I should be greater than angle C. Understood?
Yes, ma'am.
Okay, and the formula for this is to find out is nothing but sine theta 1 over sine theta 2 is nothing but n2 over n1. Okay. Or even you can say 1 over sine c is 1 and 2. Okay. So this is the formula. Any doubts?
Yes. No, ma'am.
Okay. So when the incident angle is exceeding the critical angle, then the light gets totally reflected in the medium. Where do we use it? We use this phenomena in the optical fibers. That is like this. Okay, suppose it starts traveling from this angle. Okay, then here it will be giving total internal reflection here. Now again it is made such that it is covered with two mediums. Here we are having denser to rarer, again denser to rarer. Okay, again it will travel here, again it will travel here. So it will give the clear signal, or I should say total signal on the other side without any distortions. Okay, so this is optical fiber use. Now let's do another topic, and that is diffraction of light by a single slit. Okay, now let's study about refraction of light by the single slit. So I'm showing you that part also, just pay attention.
Yes, ma'am.
Give me 1 second, it got hung. Akshita.
Yes, yes, ma'am.
Okay, can you see this picture? So this is diffraction of light at a single slit. Okay, so out of the single slit you can see that the from the P source, when the light is coming over this particular slit, what will be happening here? You will see the wavefronts pattern has been created, and they will give you a nearly parallel waves out of each wavelet, which is going to the Q point. Okay, any doubts?
No, ma'am.
Okay. So why does it happen and how does it happen? Let me explain this part to you. What happens is, when the light passes through the narrow slit, it diffracts, forming a series of the bright and the dark fringe. Okay. And I
Yes,
can show you that particular part also. Wait. Let me show you that part also. Okay, check. So now this is the diffraction pattern by the single slit. Okay.
yes, ma'am.
Okay, so here we can derive the equation for the first minima in this pattern by applying the Huygens construction that I had explained to you. So when the wavefront pass through the narrow slits, what happen is they basically propagate like this. When it comes to a single slit, it passes through this, so it creates this type of pattern. Okay, so when the wavefront passes through the narrow slit, it will propagate, and if there were a large number of wavelet sources across the slit, okay, then also it creates a wave pattern. Okay, so the resultant intensity of the central point you will see is high and barely, and then after that it is gradually increasing, sorry, decreasing, right?
Yes, ma'am.
Okay. Now, after this, let's talk about the central maxima. At the central maximum point, what happens is all the rays goes parallel. Let me show you how. See this. This is central maxima. Okay. all the line goes parallel. So the same intensity. Okay, let me show you the first maxima now. So the first maxima looks like this somewhere. Check. Can you see?
Yes, ma'am.
So this is the first maxima or minima. Okay, when I say minima, it is destructive wave. When I say maxima, it is a constructive wave. Any doubts?
No, ma'am.
Okay, so at the central maximum point, it occurs when the directly heading in front of the slit, okay, all the waves, okay, and if we take a point long away from the slit, then all the wavelets will be behaving parallelly to each other and they will be traveling same distances. Any doubt?
No, ma'am.
Okay, the wavelets have traveled the same distances and they all will be in phase, okay, giving a constructive interference and intensity will be bright. Okay, now if we consider the wavelengths that is traveling towards the first minima, then they are traveling at an angle. So they all will be traveling the same distance, but the wavelets at the top have to travel more distance in the comparison of the wavelets at the bottom one, correct?
Yes,
And
ma'am.
when these wavelets add together, they give out a destructive interference. Okay, let me give you the pattern also. You will understand. Check. So this is the pattern you observe in the minima. This is the pattern you observe in maxima. Okay, check here. This is central maxima. Then here the first maxima, second maxima, third maxima. In between the dark fringe. First minima. Can you see?
Yes, ma'am.
See this dark point. This is first minima. This is the central maxima. This is the left extreme maxima. This is right extreme maxima. Understanding or not? The picture.
Yes, ma'am.
Okay, so what happens in the minima? All the wavelets, when they are traveling, they cancel each other at the resultant point and you get a dark point. When all of them are reaching with the parallel distances and they all are having same intensity, they will give you bright light. Okay.
Yes, ma'am.
Let me give you a constructed picture for this. Just check. Check here. Okay, these are the two waves. Let's select here one slit which is having a width of B. Okay, they are going towards the first minima.
Yes, ma'am.
Okay, now see, this is the wave which is traveling. This is the wave which is traveling. Just like this here. Traveling.
Yes.
Let's take first wave and the last wave. Just take the first wave and the last wave which has been traveling. Now here you can see that this wave had traveled this much longer distance, which is lambda by 2. How much it got deviated? So from the center it got deviated an angle theta. So this is the phase difference. Correct?
Yes, ma'am.
Okay. So here you can find out your phase, that is by applying formula theta equals to lambda by b. Phase angle formula.
Yes, ma'am.
Always your theta will be measured in radians. You have to remember this. You have to measure in radians your theta. Okay. Also you can write it as sine theta equals to lambda by b. Okay. Because here
Yes.
let's have a look. B is the perpendicular and sorry, B is your hypotenuse. If I check this triangle,
Yes, ma'am.
check this
Yes, ma'am.
triangle, you will see that here this is the
Yes,
hypotenuse, this is the
yes.
perpendicular. So sorry, this is the perpendicular, my bad. Okay, so perpendicular over hypotenuse is sine theta. I had applied the formula. Any doubts?
No, ma'am.
Okay, so this is it for the day. Let's continue tomorrow, Akshita. Okay, let's meet tomorrow. And this chapter is over. Only one small topic is remaining in this, and that is the interference mathematical formula, because interference already I had explained you thoroughly. Okay,
Yes.
any doubts? You want to ask anything?
No, ma'am.
Sure?
Yes, ma'am.
Okay, Akshita. Bye.
Bye, ma'am. Thank